Hey, check this out. I created this chart for you guys. It's to compare SN1, SN2, E1, and E2. So pause the video, whatever, take a look at it. Basically, what I did was I classified according to like nucleophiles and base, right? So you could have a strong base or a weak nucleophile, or a strong nucleophile and a strong base, and then you have your different types of alkyl halides. On the very bottom, I have what some examples of those base and nucleophiles in that column. Okay, now as you have a primary alkyl halide, if you have a strong base and a weak nucleophile, then it's an E2 on the upper left. Or on the far right, if it's a primary alkyl halide and you have a weak nucleophile and a weak base, then nothing's going to happen because it's not going. Basically, your options are SN1 or E1, but it's not going to happen because it's a primary alkyl halide and you can't form the carbocation intermediate. Okay. Now, the lines down the middle of each of those columns, like SN1 and E1, those are like a 50-50 mixture. What I want to do is kind of go over some problems first, and then we'll see that chart again. But I think the chart's self-explanatory. It's just kind of organizing all of the criteria for those mechanisms. So you can use it or not. It's up to you. But pause the video and try these problems on your own. What I want you to do is basically tell me if it's SN1, SN2, E1, or E2, and then what the products are going to be. Okay, so terpetoxide is strong base, non-nucleophilic. There's our alpha carbon right here. Okay, that means that's our beta carbon, and we have a beta hydrogen on there, right? So let's swoop on that real quick. Bada bing, bada boom. Form that alkene product after that chloride leaves. Okay, and there's only one product you can form here because it's a primary alkyl halide, and you can't form different stereoisomers. We have a strong base here as well as a strong nucleophile, and it's a secondary alkyl halide. So let's take a look at the chart, right? Secondary alkyl halide. Sorry, I just wanted to write that down for you guys. Secondary alkyl halide, and then we had a strong base and a strong nucleophile. That means we have E2 and SN2 as options. Notice that line dividing them is slightly to the right. That's because we are going to slightly favor the E2 product because it's a lot easier for hydroxide in this case to grab a proton than it is to do a backside attack on a secondary alkyl halide because of steric hindrance, right? It's just much easier to grab a proton in general for a strong base. Okay, but the E2 product does still form, the SN2 product definitely still forms, and of course we have inversion about that stereocenter. And then we've got all these beta hydrogens we can grab, right? Or all two of them. And that means we're going to have a mixture of alkene products. There's this terminal alkene, and we have this internal alkene here that is trans. We also have that cis internal alkene, okay? And of course, the trans is the major product. And this is just in general the major product because we, again, have more elimination reaction than we do the SN2, okay? So the next problem, we have a weak nucleophile as well as a weak base, okay? So let's take a look at the alkyl halide. It is tertiary. All right, so tertiary, if we have a weak base and a weak nucleophile, we got SN1 and E1 for our options for products. And that's usually going to be like a 50-50 mixture-ish. And there's the first elimination product. We've seen this similar type of problem before, so we don't need to go too slow on it. There's the last elimination product. We also want to make sure we don't forget about our substitution product. There's no stereochemistry indicated in this particular problem, but we do want to remember that SN1 does give you a racemic mixture with the SN1, and with the inversion of stereochemistry as well as retention of stereochemistry. But that's not a carbocarbon. So moving on, you get the strong nucleophile as well as a strong base, and we're looking at a tertiary alkyl halide. Okay, so If we want to look at the chart, tertiary alkyl halide with a strong base and a strong nucleophile, we will have an E2 reaction occurring. Okay. Now, that's pretty straightforward. That makes sense too. If you don't even need that chart, right? You can't do backside attack. We can't do Sn1, Sn2, right? And it's a strong base and strong nucleophile, so we're not going to do Sn1 or E1. So we just form that elimination product right there. And these two beta hydrogens are the same, and so you're going to get two of those same looking things. We do have this third beta hydrogen off to the side, though, that is going to create a different product. Okay, so there's that same one. All we needed is rotation about that sigma bond. And then we've got the last one where we get that tri-substituted alkene product. When, of course, that's going to be the major product. Okay. All right, so major isomer. And then this next one, it's methanol, MEOH. That's a weak base and a weak nucleophile on a tertiary alkyl halide. We've seen this actually, so we just want to make sure that we're good on it, right? We've got Sn1 as well as E1 products. And so the Sn1 product is going to look like this, where the OME is just an O methyl group from the methanol. That's, of course, after the proton transfer. Now we want to make sure that we label all of our beta hydrogens so that way we are aware of the potential alkene products. So there's the first one. Then we can also form this one as well as this one. So there you go. That tri-substituted, of course, is going to be the major product. Now, DBU. Remember DBU? What it is. Strong, non-nucleophilic base. So right off the bat, we're thinking elimination product, specifically E2, because it's a secondary alkyl halide. And so for this one, we have stereochemistry indicated. So this is actually important. We need to practice this. We need to be able to rotate a molecule like this about that sigma bond and redraw it with all of the substituents kind of shifted. So I personally like to have my chlorine and my hydrogen in the plane of the board, if you will, or the computer screen. And so that means I have to rotate my sigma bonds accordingly. So you want to double check your work to make sure your wedges and your dashes are correct. But once you have it like this, then you can, again, this meaning the anti-periplanar position, and now you can remove that base to create that alkene product. Okay, so remember the wedges on each of those carbons, the substituents on the wedges are all going to remain on the same side, and the dashes are also going to be on the same side, just to help you draw that alkene product in the right way. So this particular problem is super fun. We want to compare the elimination products and explain the relationship. So I've actually drawn out all of the configurations already for you, because we've been done that for like a long time now. It seems like forever. So this is the relationship between these two, however, is going to be diastereomers, while the others are enantiomers. And we should know this information already. I'm just trying to fill it in for you, just to kind of make it more obvious. But I also want to draw out these hydrogens. For me personally, you won't see it like this originally, right? But fill them in for yourself if you are okay with the process that I take. Because what I do is I, again, orient them such that the chlorine or the leaving group and the hydrogen are in the anti-periplanar position in the plane of the screen, the computer screen. So I got, in this case, I put chlorine up because it was already kind of up and in the original molecule, and then I do it like this. So notice when you kind of rotate, some of the substituents stay in the whatever they were. So in this case, it was a hydrogen, um, or like I guess the wedge stayed a wedge, and then unless it was like the chlorine or whatever, right? Um, I don't know. It's just kind of this takes practice. Honestly, it's something that you want to take a look at your modeling kit when you're doing this, so that you can visualize that kind of sigma bond rotation, and what's a wedge, what's the dash, and then adjust it accordingly. Okay. So this one, sorry, I'm gonna draw all the wedges and the dashes because I know they need to be there, and then I'll fill in the substituents after. You got to think about it for a little bit, right? It takes me a second. I got to think about it. So here we go. Fill in that hydrogen for this. That means the other one's methyl, and then we got an ethyl here. Boom. And then you can also double check your work when you do rotate by checking the configuration again. So the chlorine, I'm sorry, it should be RRSS, RSSR, right? And so you can check this in a variety of ways. Either look at the carbon and see where, as you're rotating around that carbon, um, the order of those substituents. Another thing that I like to do is look at the R configurations. They should all be oriented the same way. So like on the right side, for example. So that top R and the bottom R, those have the ethyl as a dash in the back, right? And then if we look at the R on the left, we have another R on the left, and orientation of those substituents is the same, right? So we can do this for the S configurations on the left as well as on the right, and it checks out. Everything is consistent. So either I made the same error 4 times, or I guess a couple times, or it's all good. And so there's definitely ways to check your work, and you should check your work even after you get really good at this, because it's very easy to make a mistake. Okay, so now what we want to do is kind of just see what the products are, right? So we want to do the elimination reaction and then see what those products are and see what the relationships are as well. Okay, so we've already established that the top 2 molecules are enantiomers, the bottom 2 molecules are also enantiomers of one another, and then the top 2 and the bottom 2 are diastereomers of one another. Okay, so remember when we're drawing this alkene, we have the wedges are on the same side of that pi bond, at least along that double bond, right? And the dashes are also on the same side of that pi bond. So just to keep things organized and help you visualize how these products are going to look, right? So here's the last one. We've got our hydrogen on the bottom, and then we've got our other hydrogen, or I'm sorry, the methyl on the bottom. And notice the relationship between each of these. So for those 2 enantiomers on the bottom, for example, those 2 alkene products are actually the same. You just need to flip them. Okay, and the same thing goes for the enantiomers on the top. The 2 alkene products are the same. Okay, if we look at the diastereomers, however, they are different. So the bottom 2 and the top 2 are different. We have the ethyl and the methyl on one side, and then we have a methyl and a hydrogen on the other, and then it's swapped on the other alkene products. So the different stereoisomers are formed, and notice that the diastereomer reactants actually gave you diastereomer products. So this is what I wanted you to kind of envision, or I guess notice when we're talking when I mentioned explain the relationship. Okay, so this is a really fun product, really fun problem, really fun product, really fun outcome, etc. Super fun. Hashtag science, always fun. I got one joke to leave you with as we are finished with this chapter. So what do clouds wear for clothing? Do you give up? Thunderwear. Haha, yeah, so good. All right, bye. Bye.